lecture on the selecting best regression model. In the previous lecture, we have learned how all possible model involving at most k minus 1 regressors is evaluated using according to some criteria, and the best model has been selected. Well, so today we will be discussing on selection, sequential selection. So, here instead of evaluating all possible subset models, we we do not evaluate all possible subset regression models here. Here the best model is found by adding or removing one regressor in each step. So, there are three basic three algorithms of this type, sequential selection. The algorithms are backward elimination, and the next one is forward selection, and the third one is stepwise selection. Okay, so before I start talking on sequential selection, I want to recall a partial test which we discussed in multiple linear regression setup. So, we are considering the multiple linear regression setup, and we have a model with k minus 1 regressors. So, y equal to beta naught plus beta 1 x 1 plus beta 2 x 2 plus beta k minus 1 x k minus 1 plus epsilon. Okay. And by testing this hypothesis, like H naught, which says say beta I equal to 0 against the alternative hypothesis H 1, which says beta I not equal to 0. So, the meaning of this hypothesis is that basically by testing this hypothesis, we test the significance of a given regressor say x I in the presence of other regressors in the model. Okay. So, we know how to test this hypothesis. We can either use the t statistic to test this hypothesis, or also we can use the extra sum of square technique to test this hypothesis. Well, just let me recall that thing. The first one is we can test this hypothesis using the test statistic t, which is equal to beta I hat by ms residual x prime x inverse I I. So, this is the I ith element of x prime x inverse, and this follows, we know that this follows T distribution with degree of freedom n minus k, and we reject the null hypothesis, we reject H naught if mod T is greater than T alpha n minus k. Okay. So, this is the test using T test statistic. Now, this can be also tested using the F statistic, that is the extra sum of square approach. Let me talk about that. So, that is called, we will say it partial F test. Okay. Partial F test, and we will be using this partial F test repeatedly today. So, what we do is that the test statistic for to test H naught beta I equal to 0 against the alternative hypothesis H 1, that beta I not equal to 0, the test statistic is F, which is equal to SS regression for the full model minus SS regression for the full model except xi. So, here you have all the regressors x1 to xk minus 1. Here you have all the regressors except the regressor xi. So, this difference will give you the extra sum of square due to the regressor xi, or more precisely we can say that this difference is the extra regression sum of square due to the regressor xi. Well, so this has degree of freedom 1. So, you divide it by 1 and by ms residual, that is for the full model. This follows F distribution with degree of freedom 1 and n minus k. Okay. And here, so this is called the partial F test statistic, and we reject H naught if this F value is small. Sorry, we reject H naught if F is greater than the tabulated value F alpha 1 n minus k. So, rejecting H naught means accepting this one, that means xi, the ith regressor has significant contribution to explain the variability in y in the presence of other regressors in the model. Okay. So, if this difference is large, that means the ith regressor has significant contribution. So, if f is large, the difference is large, then f is large. If f is large, then we are going to reject the null hypothesis and accept the alternative hypothesis. Okay. So, this is all these things we talked before also. Let me talk about the first technique, that is called backward elimination. Okay, so it says that the basic idea behind the backward elimination is that see, we are looking for the best subset regression model. The basic idea is that you start from the full model and then in each step you reject the regressor which is less significant. Okay. So, if it is a problem with 4 regressor variables, then you start with the model with model which is having 4 regressors, and then the first step you remove the regressor which is less significant to explain the variability in the response variable. Well, so this is the basic idea behind the backward elimination, and there is some stopping criteria, of course, we will be talking about that. Well, so it says that you start with the first thing is that you start with full model, okay, and then you compute partial f statistic for each regressor in the presence of other regressor in the model. Okay. So, I will explain all these things. Let me just write down the algorithm first. Next is, see, you are computing the partial f statistic for each regressor in the presence of other regressors. So, if the f value is very small for some particular regressor, that means that is not significant. So, we look for the smallest partial f value, the regressor with smallest partial f value is removed from the model if the value is less than f out. Well, sometimes this f out is pre-specified, or this f out is equal to the tabulated value of f 0, 5, 1 and this error degree of freedom, right, and then partial f statistic are computed for this new model. By new model, I mean the model which has been obtained by removing the first regressor for this new model, and the process repeats. Okay. And here is the stopping criteria. Backward elimination algorithm terminates when the smallest partial f value is greater than f out. Okay, so let me just explain little bit and then I will illustrate this algorithm using one example. We start with the full model and then here we compute the partial f statistics. So, this partial f statistics, say for example, for the random variable for the regressor x I, that will give the partial f statistics associated with the regressor x I will give you the significance of the regressor x I in the presence of other regressors. So, this way we compute the partial f statistics for all the regressors. So, lower the value of f statistic indicates that the associated regressor is less significant. So, next we look at the smallest partial f value, and if that partial f value is less than f out or less than the tabulated value, then of course we reject we remove that regressor from the model, and again we repeat the same process until there is no partial, or there is until a step or a stage where the smallest partial f statistic is greater than the f out. Okay, that means the smallest one is also significant. So, we can't remove any more regressor from the model. Well, let me explain or illustrate this backward elimination using one example. So, I will be considering the same data, that is the halt cement data. So, we have 4 regressors and 1 response variable, and we will see which one is the best subset model according to the backward elimination technique. Well, so what we do is that we are considering the halt cement data, Okay. So, we start with the full model. So, we will first fit y as a function of all the 4 regressors variable x1, x2, x3, x4. That means, you fit the full multiple linear regression model, and the fitted model is y hat, which is equal to 62.41 plus 1.55 x1 plus 0.51 x2 plus 0.1 x3 minus 0.144 x4. So, this is the fitted model, and now what we want is that we look for the less significant regressor in this model. For that, what we do, we compute the partial f statistic associated with x1, we compute the partial f statistic associated with the regressor x2, similarly for x3 and x4. So, this is the notation f 1, 2, 3, 4. This is called the partial f statistic associated with the regressor x1 in the presence of x2, x3, x4. Similarly, also we will compute the partial F statistics associated with x2 in the presence of x1, x3 and x4 in the model, and also we will compute for all the regressors. Okay. So, we will compute F3 in the presence of 1, 2, 4, we will compute F4 in the presence of 1, 2, 3. Now, let me explain how to, just now we discussed how to compute this partial F statistic value. So, this can be computed using, this is the value of this statistic. You compute SS regression for the full model. So, I will use some other notation like 1, 2, 3, 4, that is my full model, because there are only 4 regressors in the problem, and by 1, 2, 3, 4 I mean that all the 4 regressors x1, x2, x3 and x4 are in the model. So, this is the SS regression for the full model minus SS regression for the model with random variable 2, x2, x3 and x4. Okay. Also, instead of 1, 2, 3, 4, you can write x1, x2, x3, x4, x2, x3, x4. Okay. Maybe next time I will do that by MS residual. MS residual for the full model, that means 1, 2, 3, 4. All the 4 regressors are there in that model. This is the MS residual when all the 4 regressors are present in the model. Well, so what we have to do is that we need to get this one, we need ANOVA table for the model involving 4 regressors variables. So, here is the fitted model involving 4 regressors x1, x2, x3 and x4, and here is the ANOVA table for this model, for this full model. Now, the SS regression is 2667.9, right. So, I will use this value, this SS regression for the full model is 2667.9 minus the SS regression for the model involving x2, x3, x4. So, again I need to fit this model, I need to fit the model involving x2, x3 and x4, and here is the associated, the ANOVA table for this model, and my SS regression for this model is 2641. Okay. So, I will use this value 2641.95. Now, this difference, this difference is the extra sum of square due to x1. Okay. Now, the MS residual value for the full model, again recall, so this is the full model and the MS residual value is 47.86, and look at the degree of freedom here, we have 13 datas. So, the total degree of freedom is 2, and the residual has degree of freedom 8, because of the fact that you have 1, 2, 3, 4, 5 unknowns. So, you will be getting 5 5 what is called normal equations. Okay, that means 5 constant on residual. So 13 minus 5 is equal to 8. So the residual has degree of freedom 8. Okay, and hence the regression has degree of freedom 4. Now what I want to say is that I will be using this MS residual, that is the MS residual for the full model. So 5.98, 5.98, this value is equal to 4.34. Right. Now we need to compute the other values also. Maybe I will just explain this one also. F2 given 134. So F2 in the presence partial F statistics for x2 in the presence of x1, x3 and x4 in the model. So this is regression, SS regression for the full model, that means x1, x2, x3, x4 minus SS regression for the model involving x1, x3 and x4, right, by MS residual for the full model, that means x1, x2, x3, x4. Okay. Well, so let me check whether I have ANOVA table for this one. Yes, I have. Okay, we know that this SS regression is 2667.9. Now I need a model involving x1, x3, x4. So here is the fitted model, y equal to x1, x3, x4, and the ANOVA table here. So the SS regression is 2664.94, right. So minus 2664.93 by the MS residual for the full model, that is 5.98, and this value you can check that this is close to 0.50. Okay. Similarly, you compute, I am not going into the detail for the other calculation. So F3 given 124, you can check that this is equal to 0.02, and F4 given 123 is equal to 0.04. So we have all the 4 partial F values. The first one was F1, 2, 3, 4, that value was 4.34. Okay. Now we have to see which one is the less significant. So the smallest partial F value, now the smallest, because we want to remove one regressor, the less significant regressor from the model. So the smallest, that is why we look for the smallest partial F value is, which one is the smallest? This one is the smallest. Okay, is F3 124, which is equal to 0.02. Now we can remove this. So the associated random variable is x3. We can remove the regressor x3 from the model, provided that this observed partial F value is less than the tabulated value. So the tabulated value or F out here is is f.05. So, we took alpha equal to 0.5 and the degree of freedom of this partial f statistics, it follows f distribution with degree of freedom 1 and the error degree of freedom for the full model. For the full model, the error degree of freedom is 8. Okay. So, it follows f18. So, we will find the value of f10518, which is equal to 5.32. Now, this one is the smallest partial f value, which is f3 associated with x3 1, 2, 4. This one is less than the tabulated value. So, x3 is insignificant. We can remove x3 from the model. So, we remove x3 from the model. Now, what we do is that once x3 is removed from the model, we are left with x1, x2 and x4. So, we fit a model between the response variable and x1, x2 and x4, right. So, we fit least square equation on model between y and x1, x2, x4, right, and the fitted model is y hat equal to, you can check that you have the data. So, you know how to fit multiple linear regression between y and x1, x2, x4, that is 71.65 plus 1.452 x1 plus 0.416 x2 minus 0.237 x4, right. So, this is the model after removing x3 from the full model. Well, now again what we do is that we will try to see whether we have a regressor which is less significant in the presence of other regressors. So, what we do is that we compute 3 partial f values, and there f1, what is the significant, I mean to check whether x1 is significant in the presence of x2 and x4, we compute this partial f statistics 1, 2, 4, right. We also compute f2 in the presence of 1, 4 and f4 in the presence of 1, 2, and we again look for the smallest partial f value, and which one is if that is again less than the f out, then we remove that regressor from the model. So, we will keep on doing that. Well, so what is this value? This value again I like to explain in detail. This one is obtained by computing. So, there is a little difference, that is why I want to discuss this one in detail. So, here you compute SS regression for the model x1, x2, x4 So, this is the SS regression when the model involves x1, x2 and x4 minus SS regression when the model involve only x2 and x4. So, this difference will give you the contribution, the extra sum of square or extra regression sum of square due to x1, and this divided by ms residual, ms residual for the model x1, x2, x4. So, see now this ms residual is not anymore for the full model. It now at this moment our full model is involving 3 regressors x1, x2 and x4, right. So, to get this value again x1, x2 and x4, yes, I have one ANOVA table for that. Okay. So, here is the fitted equation x1, x2, x4 and here is the ANOVA table. Now, you can check that the total degree of freedom is 12, this is same. Now, the residual has degree of freedom 9 because we have 1, 2, 3, 4 unknown parameters. So, 13 minus 4 is equal to 9, right. So, this is the SS regression for this model and this is the MS residual. We are going to use this MS residual now, right. We are not going to use this MS residual, that is for the model involving all the 4 regressors, right. So, at this moment my full model is this one. So, SS regression is 2667.79. I do not know the value of this one. Okay. You can check that you fit a model between y and x2 and x4, you find out the SS regression value, that will be 2657.9 and the MS residual value is 5.33, it is not 5.98. Okay. This one is equal to 1.86. No, I did a mistake here. This one is not 2657, it is 1846.88. The final value here is equal to 154.01, right. Now, you can check that the value of this partial F statistic is equal to 1.86, value of this partial F statistic is equal to 5.03. So, the smallest partial F value is this one. That means, if this F is less than the tabulated value, then we are going to remove x4 from the model, because this partial F statistics is associated with x4, right. So, let me write down the smallest partial F value F4 12 is equal to 1.86 and the tabulated value is F.05 with degree of freedom 1, and here now the error degree of freedom is not 8, it is 9, because see this is our full model at this moment and the error degree of freedom is, or sorry, residual degree of freedom is 9. Okay. the residual degree of freedom is 9 and this value is equal to 5.12 and this is the f out. Now, again the partial f value associated with x 4 is less than this one. So, what we do is that we remove x 4 from the model. Okay. So, the next step what we do is that see we initially we started with x 1, x 2, x 3, x 4. Then in the first step we have removed x 3 from the model. In the second step we have removed x 4 from the model. Now, we are left with x 1 and x 2. So, we now we fit least square equation y hat equal to f x 1 x 2 and this y hat is going to be equal to okay. So, that means we are trying to we will fit a model involving x 1 and x 2 only and the fitted model is y hat equal to 52.58 plus 1468 x 1 plus 0.662 x 2. Okay. So, you know how to fit how to find the unknown parameters. Now, again see we are having a model with involving x 1 and x 2. Now, we need to check whether again we can remove any more regressors from this model. That means, we have to check the significance of x 1 in the presence of x 2 and also we have to check the significance of x 2 in the presence of x 1. So, we need to compute two partial f statistics. One is f partial f statistics for associated with x 1 in the presence of x 2 and the other one is partial f statistics associated with x 2 in the presence of x 1, right. This can be done like f 1 2, this one is equal to SS regression involving x 1 and x 2 in the model minus SS regression involving x 2 in the model and this one basically it is divided by the degree of freedom is 1 by MS residual for the model involving x 1 and x 2. Okay. Well, I do not think that I have ANOVA table for this one, okay. But you can check that you fit a model between y and x 1 x 2. We have the fitted model, is it just now we have fitted it. So, once you have the fitted model you can compute the SS residual and then you know the SS total is same. So, then you can get the SS regression value, right. So, the SS regression you can check that this is equal to 2657.9 minus you fit a model between y and x 2, the fitted model is going to be y equal to 57.4 plus 0.789 x 2. Okay. So, I am giving you the fitted model. Now, you can check that SS regression value is equal to 1809.4 and the MS residual for the model involving x 1 and x 2 is 5.8, that you can check. Okay. So, the partial f value is going to be 146.52, and similarly you can check that f21. So, the partial f statistics f statistic associated with the random associated with x2 in the presence of x1 is equal to 208.58. Now, these partial f values are large. So, still we will check the smallest partial f value, the smallest partial f value is, which one is smallest? f12, f12 which is equal to 146.52, and we compare this value with the tabulated value, that is f.05 with degree of freedom 1, and if there are two regressors in the model, then if there are two regressors in the model, then the number of unknown parameters is equal to 3. So, the residual degree of freedom will be 13 minus 3. So, that is 10, okay, and this value is equal to 4.96, but this one is not smaller than this one. So, that means the model we have at this moment involving x1 and x2 both are significant. I mean both x1 is significant in the presence of x2, and similarly x2 is also significant in the presence of x1. That is why their partial f statistic value are large, and we can't remove any of them from the model. So, the backward elimination algorithm terminates here. Okay. So, here we say that the backward elimination algorithm terminates, and yields the equation, the final equation is y hat equal to 52.58. That means, the model involving x1 and x2 is the best subset regression model, 1.468 x1 plus 0.662 x2. So, the output of the backward elimination algorithm for the Hall cement data is that the subset model involving x1 and x2 is the best, okay, according to the backward elimination algorithm. Next, we will be talking about the forward selection. Okay. Okay, so what is the basic motivation behind the forward selection is that instead of in the backward elimination we started from the full model, and then in each step we try to eliminate the less significant regressor from the model. And in the forward selection what we do is that we start from a model having no regressor variable. Okay. So, initially there is no regressor in the model, and then each time in every step we try to find the most significant regressor for the response variable, and we add every step we add one regressor to the model. So, that is the just opposite of backward elimination. Okay, let me just write down the algorithm now. So, the first step is that no regressor in the model, and then all possible models. The first step is that the all possible models with one regressors are considered, and an F statistic for each regressor is computed. That means, if you have 4 regressor variable, we will start with we will consider the model one regressor model involving x1, and then the regressor model involving x2 only, and then the regressor model involving x3 only, and then the regressor model involving x4 only, and then we compute the F statistic value for each of them, and the regressor having the highest F statistic value is added to the model. Anyway, I do not have time today, so better I will start this forward selection in the, I will talk about this forward selection in the next class. Thank you for your attention.